Okay, so it's my great pleasure to introduce our second tutorial speaker for today, Professor Bjorn Poonen from MIT, and he will speak on Hilbert's 10 problem in Diophantine equations.
Okay, thank you very much. So as far as I'm concerned, it's 4:30 a.m. right now. So so let's see what happens. Yeah. All right. So I'm going to be talking about Hilbert's 10th problem, which is an example of a decision problem, and eventually, you probably know that it's an undecidable decision problem, and the source of undecidability is from the halting problem, which is sort of the prototype for most undecidability results. And so I thought I'd start by that with this. Okay, so the halting problem maybe I should first say, if you've ever programmed, you know that sometimes computer programs enter into an infinite loop. And that's usually not what you want to have happen when you write a computer program. And so wouldn't it be nice if there was if you had some meta program, some way to decide that would look at your program and decide in advance whether it's going to enter an infinite loop and warn you so you wouldn't have to run it and not know whether it's going to terminate. And so that's what the halting problem asks for. So the input to for this decision problem is a computer program. So I'll just program. Let me call it P. And just for the sake of what I want to do, let me think about programs that accept a natural number as input. So so natural number, and like any sensible person, natural numbers are starting with 0. Okay. So all right. So and then and the question that you're supposed to answer for each of these instances is, does the program halt instead of entering an infinite loop when run on this input? Okay, so for each input, the answer is either yes or no, and the task is to find a meta program that will give you the right answer in every instance. And so but unfortunately, Turing proved that this is undecidable, meaning it's not possible to have such a debugger. So so let's say it's undecidable, and I can sketch for you the argument. So the first idea is you encode programs as natural numbers. Sorry, my notes are all wet now. So encode these programs as natural numbers. These are just finite computer programs, so you could just take all their ASCII symbols of all the characters and just string them all together. And that gives you one way. So you do something like that. There'll be many natural numbers that correspond to some nonsense programs, but that's okay. They won't do much. So suppose that there is a problem. There is an algorithm for solving this. Suppose there is an algorithm. This debugger. We're deciding on every instance whether P halts on input X. So using this, you could use this as a subroutine. You could even make a new algorithm that calls this one. There's a new algorithm, I'll call it H, that has the following property. So it halts on input X.
Could you move the deck?
Yes, I can. Is that good?
Thank you.
Yeah, okay. Okay, so it halts on input X if and only if program X does not halt on input x. Okay, so how do you make this program h? So here's what h does. So it takes the input at a number x, and so it looks at program x and with input x. It doesn't run it, because if it just ran program x with input x, it wouldn't know. You wouldn't know whether it's going to terminate or not. Instead, it asks this oracle that we assume we have, we assume that there was an algorithm for deciding whether programs halt or not. So it asks that algorithm whether program x halts or not. And whatever that says it does, h does the opposite. And so it'll halt if and only if this one ends in an infinite loop. So there's a little bit of programming involved to this. You have to, because you have to know how to interpret this x as a program, and so you need a little bit of programming to do that. But you would have this h if this problem, the halting problem, existed. But now you can see that this is impossible, because if you take, if you could build this h, then you could take x to be the number of this program h, and then that gives a contradiction. Okay, so that proves that h can't exist, and so the halting problem can't exist either. Okay, so so now we have one undecidable problem, but now I'm going to use this to construct other undecidable problems. So let me now define notion of computable and listable sets. So I'm going to be talking about subsets of integers for Hilbert's 10th problem. So here's another decision problem. Given a subset, you can talk about the membership problem. So I'll just call it, just to give the problem a name, let's just call it membership in A. So the input to this problem is just an integer. And the question that you're supposed to ask for that instance is whether n belongs to the subset. Okay, so for some a, this is decidable. But for some a's it's not, and so a is called computable if there is an algorithm for solving this problem. So there's just an algorithm for membership for this problem, membership in A. All right, so now on the other hand, there's something weaker you could ask for, and this is what's known as a listable set. Okay, let me list this again. Okay, so this goes by many names. Sometimes it's also called computably enumerable or recursively enumerable. These are all the same thing. Or CE. Yeah. Okay. So anyway, so this means that there exists a computer program such that if you let it run forever, then it prints out exactly the elements of A. So, but not in any nice order, perhaps. So exactly the elements of A. Okay, so maybe I could say first that if something is computable, then it's definitely listable. Just because it's computable, you can just sort of you can just test each integer one at a time, and then print it out if it belongs to A. And so that's clear. And you might wonder whether the other implication is true as well. And we'll get to that in a second. But first, let me just give some more examples. So if you take the set of prime numbers, then that's certainly well, I mean, if you know how to, yeah. I think you all can see that that's computable. I mean, we're not talking about how fast it is. You can do a slow method for checking whether something is prime as you like. So, and that's going to be true for all the problems I'm talking about today. It doesn't matter. We're not talking about speed. We're just talking about whether you can do it at all. Here's an example. Suppose you take this set of numbers that are sums of 3 cubes. So where x, y, and z are integers. So they could be negative, so it could be cancellation here. I want to say that this is listable. And by the way, there's some rather small numbers that are not, where it's not known whether there's some cubes. I forgot what the lowest, maybe it's like 114 or something. That's not where it's not known whether it's a sum of 3 cubes. Okay, anyway, but nevertheless, yeah, so maybe it's not, so I can say this is a listable set. So how do you list all the elements of this set? Even if we don't know, yeah, so what you can do is you can print out the values of this polynomial where you loop over all of the tuples in a box. So first loop over all of the tuples, all the triples where the absolute values of the coordinates are bounded by 10. I mean, that you can do. And then you can repeat for a larger box up to 100, and then you keep going like that. So that's a computer program, and I think you'll all agree that if a number is a sum of 3 cubes, it will eventually get printed out, and that's all you need to be a listable set. But what might be hard, I mean, just because it's listable doesn't mean it's computable, because if I give you a particular number like 114, it's not clear that there's a way to decide whether it is a sum of 3 cubes. And so, yeah, in fact, for this particular set, whether it's computable or not is an open problem. I mean, it's really a number theory problem, but that's okay. Yeah, I mean, I think people expect it to be computable because it's expected that the numbers that are in the set are the ones that are not plus or minus 4 mod 9. And that's something that you can decide. So, but anyway, that's not enough. Okay, but this is just to give you a sense that there are some sets that are, yeah, they're listable, but it's not obvious whether they're computable. And in fact, there are examples of listable sets that are so complicated that they're provably not computable. And so let me give you an example of this. So this is closely related to Turing's result, and which in turn is closely related to Gödel's incompleteness result. Anyway, I think so. So anyway, this is also something from a long time ago. So that there exists, this is from the beginnings of recursion theory or computability theory. So there exists a listable subset that is not computable. Okay, so what is the example? So this is really just a translation of the halting problem. So you take the numbers of this form, where you take all possible p and x such that program P halts on input x. And and this 2 to the p3 of the x is just well, not so clever way of encoding, of combining 2 numbers into 1. So, all right, so yeah, okay, so I want to claim that this is listable. So first of all, how do you know that this is listable? What would you do if you wanted to list the elements here? Well, you just run all the programs on all the x's. And you do this all in parallel. But, all right, and then every time, and then you print the value of 2 to the p3 of the x whenever one of these whenever it halts, whenever one of these is halts. Okay, you might wonder, how do you run, if you only have one computer, how do you run infinitely many kind of programs in parallel? And you can do it. So what do you do? So okay, so parallel. What you do is you spend half of the CPU cycles on the first task, on running program 1 on input 1. You spend 1/4 of the CPU on the second task and 1/8 on the etc. Okay, and you see there's some of the tasks are running very slowly, but it's okay. If any one of them halts, eventually you'll see it and you can print it out. Okay, so yeah, and so eventually this will print out exactly the set A. On the other hand, it's not computable because, I mean, what would it mean if this were a computable set? Well, membership in this set, the task of deciding membership in this set, well, that's just the same as the halting problem. Deciding whether a number is in here is the same as, if you could do that, you could solve the halting problem. So yeah, so that's undecidable. All right, good. So, all right, so let's. Okay, any questions so far?
Excuse me?
Yeah.
Give us an example which is not listable.
Yeah, there are also examples that are not listable. So, one way to say is that there are only countably many computer programs. And so there are only countably many possible outputs of those programs. So there are only countably many subsets of Z that are listable. But there are uncountably many subsets of Z, so there are going to be some that are not listable. Yeah, do you?
Is the set A definable in natural numbers with addition and multiplication?
Sorry, say that again?
Is the set A definable in natural numbers with addition and multiplication?
Oh, is it definable? Yeah, it turns out that it turns out that all listable sets are like that. In fact, many more things that are in listable sets. There's a listable. These computable and listable are sort of are the initial parts of a hierarchy of sets that are definable in this way. Yeah, but that takes a little bit of work to understand that. But yeah.
If you replace that Z with Q, then is there any expectation?
Oh, for sums of 3 cubes in Q?
Yeah, is there any hope that that's computable?
There's hope. I mean, I think, I mean, well, actually, let's see. What?
No.
I think it's actually a theorem, actually, that every rational number is a sum of 3 cubes. So maybe we can talk about that later. So I think this is written in, for example, if you look at the book by Manin called Cubic Forms, I think in the first few pages. I mean, that's a question about rational points on a cubic surface.
So it is computable.
Yeah.
Okay.
Well, the answer is everything is.
Great.
It's a really easy algorithm to decide membership in the set because the answer is yes. Every rational number is a sum of 3 cubes. Okay. All right. Any other questions? Okay. So I think now I'm ready to talk about Hilbert's 10th problem. And Diophantine sets. Okay, maybe it's bad form to have a section that has the same name as the title of your whole talk, but anyway. Okay, so here, this is also a decision problem. And so for this one, the input is a multivariable polynomial with integer coefficients. And the question that you ask about it, so for this instance, is whether there's a solution in integers. So, okay, maybe I won't bother with it. So x is so you ask whether there is an integer solution to the equation f of x equals 0. All right, so yeah, and Well, as you probably know by now, the theorem is that there is no such solution. There's no such algorithm to decide to solve this problem. And this results from work of lots of people: Martin Davis, Sawyer Putnam, Julia Robinson. So they proved that if you look at a harder problem where you have not just polynomials, but you also allow exponentiation, so you have exponential Diophantine equations, they proved that that was unsolvable. And then Matiyasevich proved that you could actually relate exponentiation to polynomial equations. So you combine those things, then you get the undecidability. Okay, so Hilbert's 10th problem is undecidable. All right, so yeah, so I want to explain how they proved this, and to explain it, I'm going to have to introduce another notion for subsets, which is the notion of Diophantine subset. So this is defined in terms of some polynomial where one of the variables you use being a parameter. So if you have a polynomial like this in n+1 variables, then you can get a set out of it by fixing the value of the first variable to be some integer a. So you plug in that integer into the equation, and then you ask whether there's a solution to this in the remaining variables. So you ask, does there exist an x, a tuple of integers such that this holds? And so for some values of the parameter there will be a solution, and for others there will not be. And so you can take this a then is a set of good parameter values for which there is a solution. And okay, and so given any one of these polynomials, you get one of these sets. And the sets that arise that way, those are called Diophantine. So those are okay. So and the amazing theorem, which is going to imply that, so it's usually attributed to the same people. This theorem was proved via this route, and the surprising fact is that for subsets of integers, being Diophantine is the same as being listable. And maybe before I go on, let me just say why this theorem implies the undecidability of Hilbert's 10th problem. So why is this?
Bjorn,
Yeah.
question.
Yeah.
I have a quick question.
Yeah.
Is the n there fixed, or?
No, n is variable, but it turns out that actually, even if you fix n, as long as it's bigger than at least 9 or something like that, or maybe 11, I think, then I think it's 11 maybe. But anyway, if n is at least 11, even for fixed n, this is undecidable.
But then, for 10 and under, then it is, or?
Well, nobody really knows. So for 1, it's decidable, and for 2, nobody knows. And then up for 2 through 10, we're not sure. So it's kind of shocking that we don't even know it for n equal 2. But anyway, I think it's actually going to be decidable for n equal 2, but I don't know. Okay. Anyway, so okay. So let me explain how you use this theorem, this fact that Diophantine is the same as listable, to prove that there can't be an algorithm for Hilbert's 10th problem. Okay, so you start with taking. Well, it's going to use the undecidability is going to come from the halting problem again, and it's going to come from this consequence of the halting problem. So I'm going to start with this set here, the listable set. Sorry? Lift the blackboard. Okay, you want me to lift it even though they'll cover the...
Maybe that's the nowadays.
What?
Maybe you can swap the boards.
Wait, but I need to write on it still.
Maybe you can bring it all the way down, the top one.
Oh, it goes all the way down.
Yeah.
Okay.
It goes to the floor, and I checked. I'm tall enough to write on the back.
Sorry,
board,
I'm not
so-
smart enough to figure this out right now. All right. Okay. Good. Thank you. So, okay, is this high enough or? Okay. This is the listable set that is not computable. Yeah. So. Okay. So. Well, then, according to this theorem, if it's listable, then it's also Diophantine. Yeah, so it's Diophantine. But it's not computable, which means that no algorithm can decide membership in the membership problem for this set. Okay, so what does that mean? Well, I mean, being Diophantine means that it rises. This means, by definition of Diophantine, it's arising, say, from some polynomial depending on a parameter, p x. Yeah. Yeah, and so it's the set of parameter A is the set of parameter values for which this has a solution. Okay, so what does it say? No, I mean, but if membership is undecidable for this set, that means that no algorithm can decide for which values, for which integers A, the equation Pax equals 0 is solvable in integers. So the non-computability of a Diophantine set means that even in this one parameter family of instances of Hilbert 10th problem, even for that one parameter family, you can't even decide which of those have solutions and which don't. And so if you can't even do it for this one parameter family of polynomial equations, you're definitely not going to be able to have an algorithm that works for all polynomial equations. Okay? So that's how this reduction works. So okay, so now the focus is going to be on proving this. But actually, let me say one more thing. Well, okay, yeah. Let me now focus on proving this statement. Okay. Okay. So let's. All right. So now for the hardest part of this topic. So let's see. I guess maybe I should lift it. Okay, so I mean, one thing you can say is that if a set is, one direction is easy. Do you see which direction is easy? Let's see. So this way. Yeah, so we're trying to prove that Diophantine is equivalent to listable. Do you see which is the easy direction?
Diophantine is listable.
Yeah, that Diophantine is listable. So yeah, so how do you prove? Maybe I could just quickly say how that works. yeah. So let's do. So Diophantine implies listable. So how do you prove that? So, well, Diophantine means you have a set A and you have this polynomial px, and we're looking at this we're looking at this one parameter family, and A is a set of parameter values for which there's a solution. So if you have such a set, how do you list those good parameter values? So, well, you can just enumerate. It's a little bit like the 3 cubes example I gave before. You can just enumerate all possible inputs to this n+1 variable polynomial, and so you look at all pairs of n tuples of integers, n+1 tuples of integers in growing boxes inside d to the n+1, and whenever you see a solution, whenever p of a comma x equals 0, just print out the value of the parameter. Okay, so if you keep going, if you let this run forever, it'll eventually print out all the good values of the parameter, which is solvable, and therefore the set A is listable. Okay, so all right, so now I only have to do one more direction. Okay, so so now I'm going to do the listable. I mean, if you think about what this is saying, you realize pretty quickly this is going to be a hard thing to do, because there are a lot of listable sets, like anything that a computer program can output, like a set of prime numbers, for example. And given the set of prime numbers, you have to cook out some one parameter family such that, depending on a parameter, such that that polynomial equation is solvable if and only if that number is prime, or it could be powers of 2, or whatever. There are a lot of. You basically have to show that you can simulate the behavior of any computer program using a single Diophantine equation, and so that's what makes this tricky. Okay, so yeah, question mark for now. So in the remaining time, I just want to sketch some of the idea. I mean, the proof is actually, although it's completely elementary, it's pretty complicated. I mean, Matiyasevich wrote a whole book on this, on the proof of this, and I mean, he simplified it. I mean, this was originally proved in 1970, the last part, and he wrote a book in 1993 that did a little bit of simplification, but it's almost the same proof. There's some small simplifications, but I think nobody's really figured out how to simplify it much since then. I think what he wrote in 1993 is still the state of the art. So maybe that's something for us to do this semester, find a simpler way. But let me just start by giving you some of the ideas of the proof. So look, first, it's going to be helpful to be able to talk about Diophantine subsets, not just in the subsets of the integers, but also inside z to the m. And so you can also define what it means for that to be Diophantine. And it's I'm not even going to write the definition. It's the same definition. It's just you have m parameters instead of just one parameter. And you look at with the values of the m tuples, that m tuple of parameters. You ask what are the good ones for which the remaining is solvable in the remaining variables. Yeah. So for example, let's talk about. So here's an example of a Diophantine set. We take, if you take the set of pairs of integers such that x is less than or equal to y, so that's a subset of z squared, and that's Diophantine. I guess Francisco proved this for us. Well, maybe not for. Well, actually, maybe not for integers, but okay. Anyway, so first, I guess the reason this is true is because, well, I mean, how do you figure out whether x is less than or equal to y? That's the same thing as saying that there exists, let's say n1 through n4, so integers, such that x, now that we have okay, so I guess because John's in the audience, I have to make sure I get the inequality in the right direction. So I think it's y equals x plus the sum of the squares, yeah? So there's a theorem, I mean, maybe you know this theorem that every non-negative integer is a sum of four squares. And there's a converse too that says that if an integer is a sum of four squares, then it's non-negative. And so because of that if and only if, this runs through all possible non-negative integers, and then this says that y is at least x. So this is and notice that this is exactly the kind of thing I'm talking about, where you have two parameters, x and y, and you're trying to figure out for which values of x and y is this equation solvable in the remaining variables. And so it's true if and only if this is true. So yeah, so that proves that this is a Diophantine set. And I'm going to abbreviate it. I mean, it gets tiresome running all of this set of x, y, but I'm just going to say that this relation is Diophantine. That means that the set of pairs that satisfy that condition is Diophantine. And now once you have this, then you can use this relation in building other Diophantine sets. Because every time you you want to use this relation, you can always expand it out in Diophantine terms. And the other things you can do are, well, if you take this relation, that say x and y are both 0, that's also a Diophantine. In other words, the origin in z squared is a Diophantine set, and that's just because, well, that's the same as saying that x squared plus y squared equals 0. Yeah. For integers, that's true. And you can also do, so this is Diophantine. You can also do or. So this is Diophantine, and that's y is this. Well, that's even easier. So, yeah, okay. And actually, using this idea, you can combine. You can say that find intersections and unions. And finite unions of Diophantine sets are Diophantine. So, so you can combine equations. Okay, so I mean, there are lots of little things you can use. X dividing y, that's sort of obviously Diophantine, because what does that mean? It means there exists a z, it's exactly the kind of thing. You just write out what it means, and you see, oh, it's Diophantine. And you can also talk about this function. Yeah, I mean, a function is a special kind of relation, so you can also talk about them being Diophantine, the floor of x over y. So that you can, maybe I'll just let you figure out how to do that. Yeah, you just write what does that mean? Okay, anyway, so you can also do x mod y, like where this is y is some positive integer, and this is supposed to be the residue that's in the range from 0 up to y minus 1. So yeah, and then you can talk about not dividing y. Yeah, so it's not obvious that, it's not only, in fact, it's not true that just because a set is Diophantine, then its complement is Diophantine. So, but in this case, it's true because you can say this is the same as saying that x mod y is greater than 0. So if you've already defined that, you can figure out how to define greater than 0 as well. Okay, you can do GCD of two numbers, and you can do LCM. All right, so those are all, a high school student could figure out all these things. And then there's Matiyasevich, I guess he was almost a high school student. I think he was like 20 years old when he figured this out. But he figured out that, so this is the one hard thing to do. He proved that, this is the hardest part of the whole proof of the negatives of the undecidability of Hilbert. He proved that this relation in 3 variables, so x is a variable, y is a variable, and n is a variable. So this is that he proved that this is Diophantine. Which, before he proved this, some people actually, there's a famous MathSciNet review of the 1961 paper of David Trudman Robinson. So the math SciNet review, or I guess it wasn't net, but it was the math review. Oh, you have a question?
Could you move the board up?
Oh yeah, sorry. Yeah. So. Yeah, I was just gonna say that. So okay, so now it's down here. Davis, Putnam, and Robinson. They first proved that exponential Diophantine equations were undecidable, and the math reviews, the review of this paper said, okay, sure, that's okay, but you're never going to be able to use that to prove that the polynomial equations are undecidable because, I mean, of course, you can't define exponential. No, it's really unlikely that you're going to be able to define exponentiation just in terms of polynomials, because that's what you have to do if you want to prove that something is Diophantine. Okay, well, turned out he's.
You know who wrote that review?
Oh yeah, I mean you can look it up. I think it was Kreisel.
Oh, Kreisel.
I don't know.
Okay.
I don't know much about the person, but maybe you do. So yeah, Kreisel, I guess. Yeah.
I know better about the negative reviews.
Okay, so. Yeah, so I guess that means you should just watch out what you write in a math review, because you might be, especially if you're claiming that something's not going to be that something's not doable. Then,
You better prove.
What?
You better prove it's not doable.
Yeah, right. Or else you're just asking for other. I don't know if Matiyasevich knew about that review. Maybe he really wanted to prove it because of this review. I don't know. Anyway, so. Okay, so for the proof of this, all right, so see his book. Okay, that's the end of the proof. but I'll try to say a little bit more than that. So, I'll try to outline some of the ideas. I mean, I'm not even going to call this a sketch or a proof, because I'm not even going to sketch the proof, but it'll be some ideas that are related to the proof. Or maybe I'll just call it some ideas. All right, so how do you get anything that looks exponential? One thing you can do, you can say, is you take a real quadratic order. So that's a subring of a quadratic field. That's finally generated as a Z module. So you could take something like, it could be, e.g., it could be something like, I don't know, Z adjoin the square root of 3, something. So the numbers of the form A plus B times the square root of 3. That's the kind of thing that I have in mind. So it's a theorem of number theory that if you take the unit group of such a ring, then it's a free abelian group of rank 1 under multiplication. So, and the torsion subgroup is just plus or minus 1 because it's real. So there are no, and so the units, they correspond to plus or minus powers of just one number. So where the it's just the integer powers of one thing called the fundamental unit, and then you can put a plus or minus in front of it. So for example, for this ring, this fundamental unit you could take to be this number. So that's a unit, because its inverse is 2 minus square root of 3. And all the other units are powers of this one, up to sign. Okay, so and as a corollary of this, you can, units in a ring, first maybe say you can simulate this ring. Every number here you can write as a plus b times square root of 3. And so if I want to talk about elements of this, I can think of them as being pairs of integers. So if I want to talk about a variable with values in this, I can think of it as being a pair of variables, a pair of z-valued variables. And so in that way, I can talk about equations where the equations involve elements of this larger ring. And then I can talk about then the unit group, for example, is going to be something that's Diophantine. Because to say that, what is the unit? means it's an x such that there exists a y such that xy equals 1. And that's exactly what the kind of thing that's exactly the shape of the Diophantine set. And so the unit group is Diophantine, but also you can also figure out what it means for the sign for it to be positive. And so you can also prove that, for example, that this set of positive integer powers of this is also going to be a Diophantine set. So, so this is, so with a little bit of work, that's not hard. And actually what Matiyasevich in his book does, well, maybe I should say, in his original proof, he took the ring to be Z adjoin, he took the ring of integers of Q adjoin square root of 5. In that case, the fundamental unit is 1 plus square root of 5 over 2, the golden ratio. And then you take the powers of that. And the powers of that, if you write them in A plus BI form, then I think the B is like the Fibonacci numbers. So actually he proved, so in order to prove this, he did some calculations of Fibonacci numbers. In fact, he discovered a new property of Fibonacci numbers to finish this proof. But in his book he does this, which is a little more convenient. He takes this quadratic ring. So for B, for some number B, for some B, some integer, it takes it to be at least 4. Okay, so and the advantage of this is that if you take this to be your there's one unit here that's staring you in the face, namely the image of t. Because this says that t times b, t times b minus t is 1 in this ring. And so the image of t, so you can take, so this one has a unit. In fact, this generates the unit group modulo plus or minus 1. So you can take phi, which depends on b, and it'll be the image of t. Yeah, usually it's hard to figure out exactly what the fundamental unit is, but if you have a quadratic ring where you already have a very small fundamental unit, then it's usually the generator. And so here, this is built to do that. And now the key lemma is, let's see, so the key lemma, so it's going to be to prove that the set of n comma phi to n is Diophantine.
Again, just to double check that n is also a variable, so we're looking at a subset of z cubed.
And in the Matiyasevich thing, so it's a 3 variable thing, yeah. So that makes it especially hard. But even, so if n were fixed, then it would be trivially Diophantine. Like x equals y to the 5th, that's already a polynomial equation. So yeah. Actually, it's hard even for a fixed value of y. To say that x is 2 to the n, that's already a hard thing to do. In fact, even just getting the set of powers of 2, proving that's Diophantine is also hard. And it's because that's hard that Matiyasevich used these units in quadratic fields, where you already know at least that the set of the powers is Diophantine. And what that corollary doesn't tell you is how to link n to phi to the n using a Diophantine relation. And that's the key. That's the hard part. So so the key lemma is the key lemma is going to be to prove. It's essentially to prove that these set of pairs. So for let's see, for some fixed b, is the Diophantine set. So it lets you relate the number to the number in the exponent. And okay, so again, I'm not going to prove this or even sketch the proof, but here's some more ideas. So, well, one thing you can say is that phi to the n, okay, this is going to look kind of stupid. It's equal to 1 plus phi to the n minus 1. And so in particular, it's congruent to it. Well, modulo anything. But in particular, it's congruent to 1 phi to the n plus 1 squared. And the ideal, and this is the ideal generated by this. And once you know that, if you take both sides to the kth power, so kn, because this element here is nilpotent in this equation, right? You know what it is. It's really easy. It's like a 1 plus epsilon, where epsilon squared is 0. And that makes it really easy to take the kth power, because most of the terms in the binomial expansion go away. And so all you end up with is 1 plus k times this. And now if you rearrange this, you put the 1 on the other side and then divide both sides by phi to the n minus 1. You get this equation. And I divide by phi to the n minus 1, so it also changed the modulus. So this you get this relation. And now you can see some clue about how it's relating just the number k to something that's in the exponent. And so this is like how you start getting a handle on getting, I mean, you're still pretty far from proving this, but at least this is the first step. And so, yeah. By the way, actually this lemma is not the only thing, it's not really enough. What you really want to do is do this not just for one value b, but you want to do it uniformly as b changes as well. So what you'd really like is have, yeah, but the same ideas essentially work. So now you have this b that depends on b. And now you want the set of all these things. B is 4 and this natural number. And yeah, so this also is Diophantine. But it sort of follows the same strategy. Yeah, and once you have this, then now once you figured this out, once you figure out how to take powers of any one of these units in a uniform way, I can tell you now directly how to express the fact that any integer is an nth power. And so here's the trick. X is, to say this is true, is the same as saying that x is the nearest integer to the following expression. So you take phi associated to yb to the n, and then you take phi b to the n. And this is true for b sufficiently large. If b is if you take the base b to be much larger than y and n, then this ratio will be very close to the nth power of y. And the reason that this is true, is because this is because this phi sub b, if you actually solve the quadratic equation using quadratic formula or whatever, then you can see that phi sub b asymptotic is pretty close to b. It's just a little bit like this minus something is the order 1 over. I mean, it's essentially because its other conjugate is the reciprocal of phi sub b, and they add up to b. And so the bigger one has to be going to infinity, and then the other one is the inverse of that. So the other one's going to 0. And so this is b minus the other one. So, okay, anyway. So yeah, so asymptotically as b goes to infinity. So that means that if you look at this expression now, you take b and you do the same thing with yb instead of b, and you take the ratio, you're going to get something that's very close to y. And in fact, it will be y in the limit as b goes to infinity. And so for a fixed n, if you take y going to infinity in this expression, then this will tend to y to the n. And now you have to quantify that. You have to say, you don't have to let y be sorry, not, sorry, b goes, sorry, did I say y go to infinity? I want b going to infinity. If, as b goes to infinity, this goes to y to the n. And you need to make that explicit. You have to say, okay, how big does b have to be in order for this to be the closest integer to y to the n? But you can do that. It just has to be like exponentially large. But that's okay, because we already know how to say that something is exponentially large because of this relation. So you can, so yeah, so this, okay, so that's how you can get exponentiation. And well, I mean now, well, you have to do now once you have exponentiation, then it's sort of all sort of downhill from there. That's when everything is easier. For example, if you want to, so here's something you can do. For example, for a fixed, I mean not just sort of fun. You're just sort of trying to do little number theory lemmas to prove a bunch of things. For example, you can figure out the digits of some number in base b. So if you have a base, and then you have a natural number, and suppose you want to describe in a Diophantine way what's the coefficient or the digit that's in b to the d in the base b expansion. Of the given number x. Yeah, so we're writing x in base b, and I want to pick out a particular digit. And so what is this? Well, you can sort of do the obvious thing. You want to find the digit of coefficient of b to the d, divide by b to the d, take the floor, but I don't want that would give me like the whole left part of the number, all the digits to the left, but then you just take mod b to just pick out one digit. And that's what it is. And this is a Diophantine now because I can express b to the d in Diophantine terms. And so everything here is Diophantine. Yeah, so this is all Diophantine. Yeah, so, well, I mean, what else can I do? Let's do binomial coefficients just for fun. Can you think how you're going to get binomial coefficients? Yep. Did anybody figure out how to do binomial coefficients?
You introduce a really, really large number that's effectively variable, and then
Yeah. Right. So n choose k. If you want to do n choose k, this is the coefficient. This is one of the digits of b raised to the, or sorry, b. It's the kth code digit in the base b expansion of b plus 1 to the n. So, except you need to make sure that b is big enough so that you don't have carrying. So you need, so this is true for any b that's bigger than any of the binomial coefficients. So, well, okay, let's just make it bigger than 2 to the n. And then this is, you can say in Diophantine terms now, because it's just exponentiation, and we can say this in Diophantine using exponentiation too. And you can get factorials. That's just going to be, to get the factorial, you just take n to the k and divide by n choose k. And 4 of that. Well, it's really the limit of that. That's not exactly true. But if you take n to be large enough, and it turns out that n greater than this is big enough, and so that's also, if you get factorials, you can, yeah. And well, maybe I'll just say in words. So we're out of time. But part of I mean, eventually you want to use all these things to build up a universal Turing machine. You need to simulate the behavior of an arbitrary computer. And to express what it means for to do a finite computation, you want to encode a finite computation as a single integer. And usually the way you would encode a computation, if you're thinking about a Turing machine, you'd give the whole history of the tape of the Turing machine. So at each time in the computation, the tape has a certain state, and then that's some list of integers, some finite list of integers. And you want to encode that entire list of integers as a single integer. And you can do that by using base B expansion. You take B to be large enough, and then you just encode the different things at this state. But then the thing is, you have to express what it means for an integer like that to be a valid computation. So that's some complicated relation. But you can if you have enough things like exponentiation and vector or whatever, you can express that. At this point, the whole proof becomes more like computer programming than math. So I don't know. I guess that's the easy part. So, and then yeah. So that's all right. So that's pretty much the end of the proof. At least that's the end of the ideas of the proof. So all right. So thank you. So yeah. So I'll stop here.